coming to the discussion, write list of formulae. Density is given by the formula for a metallic crystal, rank, that's Z multiplied by atomic mass divided by A cube into Avogadro's number, where D stands for density of metal, Z stands for rank. You are all aware rank is 1 for SCC, rank is 2 for BCC, rank is 4 for FCC, and rank is 6 for HCP, where M stands for atomic mass, or you can say for metal molecular mass. For a metal, atomic mass and molecular mass is same because atomicity is 1. NO or Na is Avogadro number, which is 6.022 into 10 to the power 23 mole inverse. A stands for edge length. Usually edge length will be given in picometer, and if you convert this into centimeter, it is 10 to the power minus 10 centimeter. Coming to the next one, what is A cube? A, if it is edge length of the cube, then A cube is a volume of the cube. So remember, A cube is volume of the cube. Now imagine if you are dealing with orthorhombic solids. If you are dealing with orthorhombic solids, then in the place of A cube, the volume will be given by the formula A multiplied by B multiplied by C. All the three parameters multiplied together will give you volume of orthorhombic. So if you are doing the same numerical for orthorhombic, in place of A cube, you can write on A, B and C. But whenever you are doing this numerical, take care, density of metal should be in gram per centimeter cube, molar mass or atomic mass should be in gram per mole, and your A should be in centimeter, so that A cube comes out to be centimeter cube. That was for metallic crystal. If you go ahead with ionic crystal, the formula remains same. Here density D stands for ionic solid, Z stands for rank, but we know in ionic crystal we have only two types of ionic crystal. One is BCC, ionic solid cesium chloride, where rank is 1. Just check BCC ionic solid, rank is 1. BCC metallic solid, rank is 2. Two different things. Metallic solid is different, ionic solid is different. And rank is 4 for FCC ionic solid like NaCl, zinc sulfide, sodium oxide, calcium fluoride. That's what is the parameter. Other things remain same. A cube stands for volume of the cube. NO or Na stands for Avogadro number. That was the first list of the formula for density of metallic crystal and ionic crystal. M stands for ionic solid. Imagine if you are dealing with NaCl, then molecular mass will be 23 plus 35.5. If you are dealing with cesium chloride, that will be mass of cesium plus mass of chlorine, 35.5. Another set of formula that you all people should be aware is for metallic crystal. Remember, when you deal with metallic crystal, all the spheres are of the same size. If all the spheres are of the same size, then those crystals are called as metallic crystal, where if you remember SCC rank is 1, BCC rank is 2, FCC rank is 4. For SCC, if you remember, right, spheres were present like this, and from this end to this end, R and R. So that was edge length. So edge length A is equal to 2R. For SCC, there is only one example as a metallic crystal, polonium. If you see BCC, if you remember BCC, then you remember body center there is a sphere, the corners also there are spheres. That means R, R, R and R. 4R will be equal to your body diagonal. Body diagonal is A root 3. Who are BCC? BCC are soft metals. Then coming to the next one, FCC. In FCC, if you take FCC, if you remember, then there is a corner, and there is a face center. So along face center, there will be R, diameter is 2r and another r, so 4r will be phase diagonal, and phase diagonal is a root 2. Who are FCC? Hard metals, copper, nickel, aluminium and silver. Coming to the next one, for ionic crystal, there are only two ionic crystal in our syllabus. One is NaCl, other is cesium chloride. If you see NaCl, then if the green color spheres are Cl minus, remember this is called as R minus. This is R plus, this is R plus and this is R minus. So, from here to here it is edge length, and if you want to know, again if you want to see, this is R minus, this part is R plus, this part is R plus, this part is R minus. That means 2 of R plus and R minus corresponds to edge length. There will be two different kind of spheres in ionic crystal. Unlike metallic crystal, there will be only one kind of a sphere, so only one R. In this case, the formula is A is equal to 2 into R plus and R minus. Rank for NaCl is 4. If you see cesium chloride, rank is 1, and if you go across the body diagonal, then what is this value? R minus. This is R plus, this is R plus, this is R minus. That means 2 into R plus plus R minus is equal to A root 3. This is what is the formula for cesium chloride solid. So, for NaCl solid, A is equal to 2 into R plus R minus, and for cesium chloride solid, body diagonal is equal to same 2 into R plus and R minus. Remember, Na plus is present in octahedral void. Because Na plus is present in octahedral void, right, for NaCl like solids, not NaCl, NaCl like solid, radius ratio will lie between 0.414 to 0.732. For NaCl like solid, we should use this formula if there is only one data out of the two. If there is only one data out of the two, this formula should be used. In this case, if you check, there is 3 data. If there is 3 data, out of this, 2 data will be given and 1 will be asked. For cesium chloride, if you remember, cesium occupies cubic void. Therefore, radius ratio lies between 0.732 to 1. This formula should be used if out of this 2 data, R plus and R minus, they give you only 1 data. If they give you only 1 data, then this formula should be used. Right? If they give you 2 data, if you check in this formula, there is 3 terms, A, R plus and R minus. So, out of the 3 terms, they will give you 2. When should I use this formula? This formula should be used when there is only 1 data. When should I use this formula? When they give me 2 data. When should I use this formula? When they give me 1 data. When should I use this formula? When they give me 2 data out of the 3. So, that was about ionic crystal, how to deal. Now, this is mole concept. If you are aware, in mole concept, you can connect molecule with mass by a concept. 1 mole of any substance, I am writing it here, 1 mole of any substance stands for m gram, and m gram stands for any number of particles. From this you can connect particles and the mass, or particles and the mole. Number of unit cells. Z particles, rank number of particles stands for 1 unit cell. Then n particles stands for how many unit cells? How many unit cells? If you cross multiply, number of unit cells which contain n particle is given by the formula n by z. This formula can be by hearted to find number of unit cells. Again, number of unit cells carrying or containing n particles is n by z, when n is number of particles and z is a rank for that unit cell. Number of unit cells in 1 gram of substance. How many unit cells are present in any particles on that ground? n A by z, only in the place of n we have put now n A. where Na stands for Avogadro number. We are aware that 1 mole stands for m gram of the substance, and m gram of the substance contain Na particles. Na particles. M gram of the substance contains Na particles. So, 1 gram of the substance contains how much? 1 gram contains how much? So, if you cross multiply, 1 gram contains how many particles? Answer is Na by m particles. Na by m particles. Now, Na by m particle, if this is the number of particles, that is n, then 1 gram of the substance will have how many unit cells? Number of particles divided by Z is number of unit cells. Again, check, m gram of the substance contains how many particles? Na particles by mole concept. So, 1 gram will contain how many particles? Na by m. So, the number of particles, instead of Na, you have Na by m. Whatever is the number of particles, now your number of particles is Na by m, divide that by Z, that is number of unit cell in 1 gram of the substance. So, you can by heart this formula also, it is Na by m into Z. Remember, 1 gram has how many particles? Number of particles present in 1 gram is actually Na by molar mass. So, only in the place of n we have put Na by m and divided by Z. Number of unit cells in W gram. If 1 gram of substance have Na divided by m into Z, then W gram of the substance will have W multiplied by Na divided by m into Z. So, this is what is the number of unit cells. W, that is mass of the substance, multiplied by Na, that is Avogadro number, and this. Remember again, Na by m is for 1 gram. If you take this is number of particles and you divide number of particles by Z, that is number of unit cells in 1 gram. But you want in W gram, so multiply by W. You will get the answer of number of unit cell present in W gram of the substance. Then you are aware corner contributes 1/8 to the cube, face center contributes half, body center contributes 1, edge center contributes 1/4. About voids, position of voids. Where is octahedral void present? It is present at body center and edge center. Where is tetrahedral void is present? It is present on body diagonal. If you remember, if this is body diagonal, this is corner and this is body center, then tetrahedral void is present here. So, tetrahedral void is the center of body center and corner in FCC. You are aware FCC is also known as CCP, that was position of voids. What about number of voids? For FCC or HCP, now we are saying HCP also, you know FCC and HCP have same packing ratio of 74%. If number of spheres are n, then octahedral voids are also n and tetrahedral voids are 2n, and total number of voids will be n plus 2n, that will be 3n. Total number of voids. Number of spheres n, number of octahedral voids n, number of tetrahedral voids 2n, total number of voids will be 3n. Coming to the next discussion. This type of discussion is important for ionic structure. If your radius ratio, that is the size of cation to that of the size of anion, or radius of cation to that of radius of anion is less than 0.11155, then your sphere is surrounded by only 2 other spheres, coordination number will be 2. If your radius ratio lies between 0.155 to 0.225, then your void will be triangular void and the coordination number will be 3. Boron is present in triangular void surrounded by 3 oxide ions. If it is 0.225 to 0.414, then your cation will be present in tetrahedral void. So, if you remember in zinc sulfide, sulfide makes up FCC and zinc occupies tetrahedral void and its size is between 0.225 to 0.414. If your radius ratio is 0.414 to 0.732, then your cation will be present in octahedral void. Anyone who is present in octahedral void will have coordination number of 6. Here in this case, if you remember, Cl minus makes up FCC and Na plus occupies octahedral void. Na plus oxa, right, occupies octahedral void with coordination number of 6. If your radius ratio lies between 0.732 to 1, better to remember 1, then coordination number is 8. Example, cesium chloride, where chloride was making SCC and cesium was present in cubic void. So, right, that's again discussion in NaCl, Cl minus occupy FCC. What do you mean by FCC? 8 corners and 6 face centers, and Na plus occupies octahedral void. What do you mean by octahedral void? One body center and 12 edge centers. Remember that. If you want to know exact size of triangular void, it is 0.155 multiplied by R. What does that capital R stands for? Capital R stands for radius of the spheres which make triangular void. Again, size of tetrahedral void. If you want to know exact size of tetrahedral void, it is 0.225 of capital R. What is that capital R? It is the radius of the spheres which make up the tetrahedral void. Exact size of octahedral void is 0.414 multiplied by R, where capital R again stands for radius of the sphere, and exact size of cubic void is 0.732 multiplied by R. All such numbers have to be remembered. All these numbers have to be remembered, even the exact size and the range. Algebraic shortcuts that you should know. If edge length is given as 400 picometer, remember that's 400 multiplied by 10 to the power minus 12 meter, picos value. Convert this into centimeter. If you convert this into centimeter, 10 to the power 2 centimeter, that is nothing but 400 multiplied by 10 to the power minus 10 centimeter. Conclusion, whatever is this, just multiply by 10 to the power minus 10, you will get centimeter. Again, if you rewrite, can I say it is 4 into 10 to the power minus 8 centimeter? From this, we realize if your edge length is 3-digit number in picometer, convert this into 1-digit number with decimal place, multiply by 10 to the power minus 8, that is your edge length in centimeter. So, next time when you have edge length as 320 picometer, we can directly write on 3.2 into 10 to the power minus 8 centimeter. Similarly, if edge length is given as 2 angstrom, then same logic, write on 1 digit and write on 10 to the power minus 8 centimeter. That means more often in the chapter of solid state, edge length will be 1 digit with some decimal places multiplied by 10 to the power minus 8 centimeter. So, whether it is an angstrom or whether it is a picometer, you can conveniently write down. Next thing, you should be aware, density of heavy metals will be usually 8 to 17 gram per centimeter cube. This is for heavy metal. Density of light metal, very light metal, can be like this as 0.7 to 4 gram per centimeter cube. Even ionic solids have density in this range. Whenever you want to use Avogadro number in the chapter of solid state, you can very well write down 6 into 10 to the power 23 like this. And you want to do cube root. How to do a cube root? Remember, 1 cube is 1, 2 cube is 8, 3 cube is 27, 4 cube is 64, 5 cube is 125. So, somebody asks you cube root of 1, you know it's 1 only, cube root of 8 is 2. Now, imagine somebody asks what is cube root of 6. Now, we don't know the value, but at least we know it will be between 1 to 2. At least that much guess you can do. Cube root of 27 is 3. But now somebody asks what is a cube root of 20? We know 20 lies between 8 and 27. 8 cube root is 2, 27 cube root is 3. So, 20 cube root will be between 2 to 3, but closer to 3. Similarly, somebody asks what is cube root of 100? Think what is cube root of 100? We are aware cube root of 125 is 5, cube root of 64 is 4, 100 lies between 64 and 125. Therefore, your answer will be between 4 to 5, but closer to 4. So, these were all the algebraic shortcuts that you should be aware while dealing with numericals of solid state. So, we come to the numericals of Cation vacancies. When one strontium ion enters into NaCl crystal, we are aware 2 Na plus ions. 2 Na plus ions are removed. Why? Because one strontium ion has a charge of 2 plus, which is equivalent to 2 sodium ions, of which one sodium ion's position is taken by strontium, one sodium ion which is lost, that position is taken by strontium, and the other place remains vacant. That means there is one cation vacancy. So, correlation, one strontium ion will cause one cation vacancy and will remove 2 sodium ions. Using this relation, we will be solving numericals. Imagine if there is one aluminium ion entering into sodium chloride crystal, then it will remove 3 sodium ions from the system, of which one sodium ion's position aluminium will take and will create 2 cation vacancy. So, one aluminium ion will create 2 cation vacancies. But why the word imagine? Because this is a hypothetical example. The real examples are with only divalent ion, not with trivalent ions. So, this is imagination. So, one aluminium ions will remove 3 sodium ions and will create 2 cation vacancy. Using this, we will be solving various numericals. Numericals based on metal deficiency defect, in which metal is lesser in number than an ion. In this case, let the number of oxide ions be 100. If oxide ion is 100, then we know this type of deficiency defect is there because system contains both ferrous as well as ferric ions. So, if oxygen is 100 or oxide ions are 100, Fe is 93. If Fe is 93, let ferrous be X. But why ferrous X? Because they are asking for ferrous. Then how much will be ferric? 93 minus X, because total Fe ions are 93. Total positive charge and total negative charge is equal to 0 for any system to maintain neutrality. Positive charge is due to ferrous and ferric ions, while negative charge is due to oxide ions, and total is 0. So, X ferrous has a charge of 2, remember that. Ferric has a charge of 3. Number of ferric ions are 93 minus X. So, total charge on ferric ions is 93 minus x multiplied by 3. 100 oxide ions multiplied by minus 2. If you solve, you will get the value of x as 79. So number of ferrous ions will be 79 divided by total 93. So that's how you get percentage, and the answer will be definitely common sense more than 79, and that will be 85 percentage. This is what is the logic of solving metal deficiency defect. In metal deficiency defect, consider the anions by some number, more commonly 100. Natural Fe will be 93. Whatever they are asking, put it as x. Remaining will be 93 minus x. And by using charge neutrality equation, you will be able to get the unknown. That is the logic of solving numericals based on metal deficiency defect.